Oil electric stress 3D. In previous example we have simulated two-dimensional problem and calculated electric stress distribution in the oil gaps near the end of the winding. In this example we will build three-dimensional model and calculate electrical stress in the transformer oil. Again we have the grounded core, three-phase winding, oil, press board insulation and the tank. If you check the electric circuit, you will see that the voltage changes linear along the winding height. At the bottom the voltage is 0, at the top the voltage is maximal. In QuickField you can specify electric potential distribution as a function of coordinates. The voltage changes in time, but I'm interested only in the peak stress values, so I will simulate electrostatics problem and specify peak values of voltages. Three-dimensional model can be imported from the CAD system, or you can construct three-dimensional model by extrusion. This is a simplified configuration of the transformer insulation, and this geometry model is suitable to demonstrate three-dimensional extrusion approach. Okay, let's start QuickField now. I create new problem, transformer oil. Next. Problem type is electrostatics. Length units are centimeters. And model class is three-dimensional extrusion. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. I should draw the plane geometry model here, and then I can assign heights. Okay, let's switch to insert mode, choose the line type half arc, and draw two arcs to construct a circle. Let's zoom to fit, switch to select objects mode, click inside the circle to select it, and here in the properties pane you can assign levels. I will add level 0 and 50 centimeters. Okay, now let's build the finite element mesh and toggle two-dimensional, three-dimensional view. Here you can see the leg of the transformer core. Okay, let's switch back to the two-dimensional view and add two legs more. Click to select, right click, duplicate selection, displacement by 44 centimeters. And I need two more core pairs. Okay. Again, now you see there are three circles here. Let's build the mesh and again toggle two-dimensional, three-dimensional view. Good, we have three legs. Switch back to the two-dimensional view, and here I should draw the horizontal lines. I'd better adjust the grid settings. Let it be 1 centimeter. Okay, switch to insert mode. This time it will be the straight line. Click and drag here and here. That would be the core top and bottom yokes. Switch to select mode, select the yoke and assign heights. Minus 20 centimeters and 70 centimeters. Build the mesh, toggle the view. Oh, I need to assign heights to these bodies. Okay, switch back to the two-dimensional. For these and these I should assign heights 0 and 50. Three-dimensional view. Now that's good. In fact, not all these bodies are the core. I should assign labels to distinguish bodies. To select the body, I should click it and the face is selected. To select the body, I should click the selected face again. Now the body is selected. To select multiple objects at the same time, hold the Ctrl button pressed. Now I can select another body. These two bodies probably the oil, as we have the transformer immersed in the oil. So I assign the label here oil. Now let's hide these bodies. And all the remaining bodies are the core. I select them all and assign the label core. This time I have selected not only the bodies, but the faces and the edges and the vertices. And I know that the transformer core is grounded, so the faces of the core has 0 electric potential. I assign the label grounded, and for this label I will specify 0 electric potential. OK. For the oil I will specify electric permittivity, which is 2.2, and for the core I would not specify any value because there is no electric field inside the core. OK. Now let's switch back to the two-dimensional view and draw the tank. Switch to insert mode, click and drag here and here. Now let's switch the line type to be the half arc. Okay, let's zoom to fit. That would be the tank. Again, I should build the mesh and I should assign the height. So switch to select objects mode, select everything and assign the heights minus 30 centimeters and plus 100 centimeters. Okay, toggle to three-dimensional view. The tank is filled with oil. To assign the label to the body, I should click to select the face and then second click to select the body. This is the oil. Now let's hide the oil. These objects are oil. Oil. And these objects are oil. Right click, hide the oil. Okay, this is the core and the oil. Let's unhide the oil and let's make it transparent. We have the core inside the tank filled with the oil. The tank is grounded. Let's again make the oil opaque and select the faces. Top, bottom and side faces, and the face on the other side. I will give them the name tank and assign 0 electric potential. OK. This way you can add more and more elements to the model. Let's add the winding. Switch to insert mode, choose the line type to be the half arc and draw arcs here. This would be the insulation layer. This would be the low voltage winding. Again the insulation layer and the high voltage winding. And again the insulation layer. Now let's switch to select objects mode and assign heights. I select the winding and assign levels 42 centimeters and 48 centimeters. Okay, let's build the finite element mesh. Toggle to three-dimensional view. Hide the oil. And all these objects are oil. Hide them. And these objects are oil. Hide them. And here we have the winding structure. This is the insulation. Hide. This is the high voltage winding. HV phase A. Hide. This is the insulation. Hide. And this is the low voltage winding. Low voltage phase A. Hide. And again, this is the insulation layer. And we have to assign labels to these parts. This is the low voltage. Click, click. This is the high voltage. Hide. Hide. I will hide the core. I will hide the oil. So this is generally the insulation structure. Select all these blocks and assign the label insulation. Okay, let's check the model. Unhide all. Select the oil. Make it transparent. We have a core. We have the insulation. The insulation electric permittivity 4.5. Okay. Let's hide the insulation. We have the high voltage winding. There is no electric field inside conductor, so I do not specify electric permittivity value here. And the same is true for the low voltage winding. Instead, I should specify the electric potential distribution on the winding face. So let's hide everything but the high voltage winding. Here it is. Let's select the winding faces and assign the label phase A, high voltage. For these phases I can specify electric potential. Remember, electric potential varies with the winding height. It is maximum at the top of the winding and 0 at the bottom of the winding. So I type in the equation here. The potential value is 6 kilovolts, which is RMS value, and I need to specify the peak value, so I multiply this by square root of 2 and multiply it by the z coordinate and divide by the winding height, which is 48 centimeters. I should type in values in meters here. This way, at the bottom where the z coordinate is 0, we will have 0 electric potential, and at the top where the z coordinate is 0.48 meters, we will have the maximum electric potential. And the same for the low voltage winding phases. Hide all but these, select the phases, assign the label to the phases, phase A, low voltage. And for the phases I specify electric potential. 400 volts multiplied by square root of 2 multiplied by Z divided by the 0.48. Okay. Same way you proceed with the phase B and the phase C. Here is the completed geometry model. I have drawn the winding structure for the phase B and the winding structure for the phase C, and I have assigned heights. Now if we toggle two-dimensional to three-dimensional view, we can see the three-dimensional structure. Here we have the tank, which is grounded. We have the oil, and if I hide the oil block, I can see the internal structure. The core, which is grounded. Hide the core. And we have the phase winding, which are insulated. We made the insulation transparent. We can see the coils inside. We have not specified any electrical properties for the coils. Instead, we have specified electric potential distribution on the coils' faces. You see the potential depends on the Z coordinate, so it will change in space. And for the phase B, we have specified the same equation with the phase shift of 120 degrees. And for the phase C, the same equation with the phase shift of 240 degrees. The last step before you can run the analysis is to build the fine entanglement mesh. You can do this in 3 stages. First, build the mesh on edges. Then, build the mesh on faces. And the last, you build the mesh in volumes. Once the mesh is constructed, you can save all problem files and run the analysis. The problem has been solved. Let's take a look at the results. Here you can see the electric potential distribution on the tank, which is 0. To look inside, I can hide some oil layers. Right click, hide. Let's for now hide all oil blocks. Right click, hide. Now you can see the electric potential distribution on the core faces and on the insulation. Let's hide the insulation. As you see, the electric potential changes with the winding height. Let's select this edge and take a look at the XY plot. Indeed, the electric potential changes linearly with the winding height. We have the maximum electric voltage at the top and 0 electric voltage at the bottom. Well, go back to the field picture. Here you can choose the value to display. I will change the displayed quantity from electric potential to electric field strength. In fact, I'm not interested in the electric field strength in the conductors. I'm interested in the strength in the oil. Let's unhide all. To look inside, I will use the cut by plane tool. I will change the plane direction and I will change the plane orientation. And let's hide the plane. Let's hide the geometry. Now you can see the electric field strength distribution in the oil gaps and in the insulation. You can get exact field parameters in any point. Just use the probing tool, click the point, and here you can get the electric field strength and the electric potential value and the permittivity value. So now you know I have clicked in the press board, and if I click here, I will get high electric potential in the oil and the electric field strength in the oil. You can also take a look at this picture in the two-dimensional section view. Here again you can adjust the field picture, choose the value to display. You can build contours here. And take a look at the field distribution along the contour line. electric potential, electric field strength, and the exact values you can see in the table. Coordinates, electric potential, electric field strength. If you search for the electric field stress in a transformer oil example on our website, you will find the page. Here you can read about problem setup, browse the solution section, take a look at the resultant picture and download the simulation files. The simulation files may be opened and viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.